Ah, Good day, guys. Today we'll be discussing about chemical carcinogenesis. So this is the first part of carcinogenesis. You'll also be discussing about radiation carcinogenesis and microbial carcinogenesis. So briefly about chemicals that can cause cancer. So let's start with a case. Imagine you have a 78-year-old Navy veteran with a 600 pack per year history of cigarette smoking who presents with cancer. And during his military career, he gives a history of being exposed to asbestos. Given his environmental exposure to both tobacco and asbestos, to which cancer do both of these carcinogens contribute? Is it bladder? Is it bronchogenic, throat, esophageal, or mesothelioma? So, what are these carcinogens that came in the question? Basically, we will revisit this question at the end of this discussion and you can reanalyze your thoughts. So this Percival Pott, who was he? He was one of the first few people who associated a chemical with a carcinogen. For example, he encountered these children who are called chimney sweeps. They were called chimney sweeps because they cleaned the chimneys and they very commonly presented with scrotal skin cancer because they were exposed to soot. What is soot? Soot is that carbon leftovers from the burning of firewood. So Percival Pott was one of the, and this is in 1775, in the year 1775. So there was a first association of a chemical that can become a carcinogen. So what is carcinogenesis? It is otherwise called oncogenesis. It is called tumorogenesis, basically the genesis of cancer, pathogenesis of cancer. And it is the mechanism of induction of a tumor, where a tumor starts. How does a tumor begin? And these agents that cause the induction of tumors are called carcinogens. So they not necessarily, as we already discussed, can be chemical, can be radiation, and can be microbial. So in chemical carcinogenesis, you need to know that these chemical carcinogens are all around us. And one of the most common ones is polycyclic aromatic hydrocarbons that come from burning of fossil fuels. They are highly reactive electrophiles. What do you mean by highly reactive electrophiles? Highly reactive electrophiles are very electron deficient, electron hungry compounds. And what is an electron rich component of our cell? It is the DNA and the RNA. So they are highly attracted to our DNA RNA material. And when they act on them and cause permanent changes, they cause permanent changes to such genes that are called proto-oncogenes that require activation, a mutation that makes them oncogenes, and anti-oncogenes such as P53 that protect our genome. So mutations to a proto-oncogene or a mutation to an anti-oncogene, right? They can all lead to tumorogenesis. Now this occurs in three steps: initiation, promotion, and progression. The initiation step is the most important step in chemical carcinogenesis because without initiation, you do not have promotion or progression. So, initiation is when the chemical carcinogen acts irreversibly, sudden, in a very short duration, and causes a permanent change to your DNA. But without this initiation, you don't have promotion or progression. But at the same time, if you do not have promotion and progression, the initiation step can end abruptly in not forming tumors. We will see. Whereas in promotion, you have cellular damage. You have, as in the damage has already been done, an irreversible damage by the initiator. Now a promoter acts on it, and this promoter causes reversible and slow. So the longest phase in initiation and promotion progression is actually promotion. Promotion can take years for a tumor to develop. Multiple other mutations can occur based on the dosage, based on the duration of the exposure of the promoter, and unlimited cell proliferation occurs at the end of promotion. Progression is proliferation of these mutated cells, acquiring more and more mutations, specifically these P53 mutations, the RAS mutations. So these mutations now give it a phenotypic characteristics of malignancy. What do you mean by phenotypic characteristics of malignancy? The patient clinically presents with cancer. So in a diagrammatic format, you have normal cells. They undergo initiation. So the chemical acts and you have initiation. You have DNA damage. Now this can lead to one, the cell realizes that it cannot repair its DNA and therefore undergoes apoptosis, programmed cell death, as you already know. The second one, it can repair your DNA and it can go back to being a normal cell. Or the worst outcome, it can undergo proliferation and start becoming a cluster of these mutated cells. Now they at that point also can undergo apoptosis, or otherwise they can continue proliferating, acquiring more and more new mutations and finally form a cancer cluster. So this is another form of it. This is in your textbook also. So you have, what are these chemical carcinogens that act? So they can either act directly on DNA, right? They don't require any metabolic activation, but indirectly acting ones, they are more dangerous. They are procarcinogens. They are more harmful and more common, right? And more active once metabolically activated. So where are these dangerous indirectly acting carcinogens activated? In the liver. Each of us have a set of cytochrome P enzymes that are very specific. They are highly polymorphic. They are genetically decided, right? That is why some people are prone to certain cancers and some people may not be. Uh, so they are activated in the liver and then they form these reactive electrophiles. This is a catchword. Somewhere in your answer, you must mention about reactive electrophiles because that is the active form of the chemical carcinogen which actually mutates the cell. It attacks the target molecule, mainly the DNA, causes permanent damage to it, then clonal proliferation, and finally the phenotype of cancer. Once again, there are three steps: initiation, promotion, and progression. You require initiation. Only then will promotion and progression be effective. So, among the directly acting, you have two types. You have alkylating, for example, cyclophosphamide, and acylating, which is imidazole. They are weak initiators. So, as nature has it, these directly acting initiators are actually very weak acting. But the indirectly acting examples are polyacyclic aromatic hydrocarbons, vinyl chloride, asbestos, and metals like lead, arsenic, and these are pro-carcinogens. They are they are broken down by the cytochrome P450 system of our liver cell, located where? In the endoplasmic reticulum. So in initiation, a little more detail. You have proto-oncogenes such as RAS, which is responsible for cell proliferation, and anti-oncogenes such as P53. So an example, right? P53 is mutated in hepatocellular carcinomas, right? Promotion, here the characteristics, they do not cause sudden change. Unlike initiation, initiation is sudden, permanent, irreversible. Whereas in a promotion, it is all the opposite. It is slow, it is reversible, right? And it requires something called promoters. Examples for promoters, you have hormones, you have phenobarbital, you have artificial sweeteners, and they can cause additional changes to a cell where the cell learns now to clonally proliferate with the permanent mutation. So I just put it in a tabular form, the difference between an initiator, the first step, and the promoter. Mechanism is the inducer of mutation, but promoters are not mutagenic. The dose, an initiator, is a single shot or a short duration, whereas this one is repeated and long. The response of the cell is sudden and slow in promoters. The change that occurs is irreversible and permanent in initiators, whereas it is slow response in promoters. Sequence. First comes initiation, because if initiation does not happen, promotion has no significance in tumorigenesis. Whereas here it follows initiation. Effectivity, you need either large doses in a short duration or a short dose in a large over a long period can also initiate tumors. Whereas in promoters, they don't not an effective agent alone, acting alone. It requires the initiator to cause the initial mutation uh, before the tumor process. The molecular changes, you have the RAS oncogene, you have the P53 oncogene, whereas here you have only clonal multiplication of these cells. Whereas in initiation, you have specific mutations that occur to these crucial cells that regulate the cell cycle. So the chemical carcinogens and the radiation carcinogens are all initiator carcinogens, whereas hormones and esters and your these artificial sweeteners, they are all promoters. So the last step of chemical carcinogenesis is progression. You've already initiated the mutation, the cell is already proliferating with the same mutated DNA, and now comes proliferation. The mutated proliferated cell shows phenotypic features of malignancy. Their morphology, the biochemical composition, the molecular features of malignancy are all different from a normal cell in the same organ. The initiated cell starts to proliferate rapidly and it acquires more adaptive mutations. Now the tumor will start learning how to grow its own blood vessels, how to grow rapidly, how to avoid the immune system, right? So this is an example of an hepatocellular carcinoma. And very commonly, hepatocellular carcinomas are seen with viruses, and but also they are associated with a biological fungus called aflatoxin. Okay, the fungus produces an aflatoxin which can actually be carcinogenic to the liver. So here you have examples of these various carcinogens. When you see this ring, I'm sure you recognize it. It is the benzene ring, all benzene derivatives. Then you have the polycyclic aromatic hydrocarbons. Here you have asbestos, you have vinyl chloride, you have nicotine, and you have aflatoxin, a fungus that grows on grains. This is tobacco related lung carcinoma, right? Can you see all these black deposits and this large tumor that has already almost replaced half of the organ? So a little bit about chemical carcinogens. Um, if you're asked about the directly acting alkylating um, carcinogen, it's cyclophosphamide, one of very commonly used cancer drugs. They are immunosuppressants, they bind to DNA, and they disrupt cell cycles. They are weakly acting, but they can act very well if when it is given in high doses. They can cause leukemias, lymphomas, and many other cancers. Among the indirectly acting, the most common is the polycyclic aromatic hydrocarbon, benzopyrene. They are highly potent procarcinogens and they can cause cancer in the region of contact, tobacco in smoke, in tobacco smoke, in broiled or these kebab-like food protein that is exposed to very high temperatures to cause burnt up carbon on the meat, and these can cause bladder and lung cancers. So coming back to our history where we started, you have a 78-year-old Navy veteran with a 600 pack year history of cigarette smoking. He presents with cancer and he was also exposed with asbestos. So what do you think is your answer? The answer is bronchogenic cancer.